following on from the previous video, we've established that this here will work when n is a positive whole number, like 1, 2, 3, 4, 5, and so on. And it even works even when n equals 0. In this video, we're going to consider negative when n is negative. So, for example, x to the power of minus, let's say 5, or x to the power of minus 6. We know that when you differentiate this, it becomes this here. But we don't fully understand why this is the case. You see, so far we've seen that it's true for all when n equals these. But what happens when n is a negative number? What happens when the index is a negative number? Okay, so to understand this here, we're going to use the quotient rule here. Remember the quotient rule is this thing here. Remember that this is definitely true. That the quotient rule is definitely true because we've proved that. So you have to accept that this here is definitely true. Okay. Now, if you want to understand the case when x to the power of a negative number, think of it like this. We're going to try and differentiate this here. Okay, but rewrite this as remember from our knowledge of indices. When you have something to the power of a negative number, you can immediately jump to this. Okay, so really this n here is like a positive whole number. Okay, so we are trying to differentiate this here. So we're going to visualize this thing as this thing here. Now looking at it like this here, let's use the quotient rule here. Okay, so this is our u here. Okay, and this here is our v. So really v is x to the power of n, and u here is just 1. Okay, so now imagine this here is u. Okay, and this here is v. So now if we want to differentiate this, we're going to use the quotient rule here. So let's just blindly follow the quotient rule. So here, differentiate the u. Remember, u is this, u, and this here is v. Okay, so this here is u, this here is v. Let's just blindly differentiate this using the quotient rule. So, hang on. So, differentiate u. When you differentiate u, that would be when you differentiate 1, it will be 0, and 0 times v here, which is x to the power of n here. This whole thing here later on will be 0. Okay, this minus here is minus here, and then leave u the same. So that's leaving u the same. So that's 1, and then times the differential of the v. So times the differential of this, which will be n x to the power of n minus 1. And remember, we know that you can differentiate this thing here when n is a positive whole number. Okay, because yeah, we know that we know that this here you can differentiate this. So that becomes this here, but we just don't know when it's a minus. We don't know if we can differentiate this. We don't know how to yet, but we do know from the binomial expansion that you can always do it when this is a positive whole number. So this here, remember, n is positive. Remember, okay? So yeah. So when you differentiate this, when you differentiate v here, it will give you n x to the power of n minus 1, because we know you can differentiate it when it's a positive whole number. Let's say 8 here, we can do that, but we don't know if you can do this. This is what we're trying to establish. Okay, but anyway, when you differentiate the v here, it will give you this. Okay, and now v squared here. V squared here will be this thing squared. So let's just write it as this thing times by itself. Okay. So now this thing here will become 0. So this is your 0 here, and then minus 1 times this thing here will be just this thing here. Okay. So this minus here is this minus here, and then this bit here is this bit here. And when you have x to the power of n times x to the power of n, remember from our knowledge of indices, if you have this here, then you add a and b. So when you have n, add n, that will give you this 2n. Okay, so remember we started out. Hang on, we started out with this here. Okay, and remember by n here is for all hang on, n here is for 1, 2, for positive whole numbers. Okay, because if you put 2 into here, the n here is a positive. Remember that n has to be one of these positive whole numbers here. Okay, so reimagine it as this here. So now we turn the minus into a positive, and positive we know how to deal with the positive. We just don't know how to deal with n equals minus. So we would reimagine this as this here. Okay, and then blah 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 from using the quotient rule here, it takes us to this stage here. Okay, so from this stage here, hang on. From this stage here, imagine this here as this. Hang on. Imagine this as 1 over x to the. Imagine this as one block timesing this block here, x to the n minus 1. So when you multiply these two together, this here gets multiplied to the top. So imagine this whole thing here is like this thing here. Now this block here, you can think of it as this to the power of minus 2n. So now you've got this block times this block here. So basically this thing here becomes this. Okay, and then let me think. Yeah, so here you've got this block multiplying with this block here, multiplying with this block here. Let's move this block out here. So that's me. That's us moving this thing out here, and then this. Hang on. So here you've got one block multiplying. These three blocks are multiplying with each other. So we're just moving this out in front. Okay, and then that will give you the, well, here you've got same base multiplying with same base. So you're going to get you're going to get this, add this thing here. So if you look at this here, remember you've got this thing multiplying with this thing multiplying with this thing. You can merge these two together. So when you have x to the power of a times x to the power of b, you would get a plus b. So this is your a here, this is your b here. So look at this, minus 2n. So and then you remember if you multiply the two together, you've got to get this bubble here, add this bubble here. So you've got to add n minus 1. So here you've got minus 2n plus n. That will be minus n, and then you've got your minus 1. So after all that there, if you differentiate this thing here, it will give you this. Now here's a key step. So at the moment, hang on. So at the moment you've got if you differentiate this thing here, it will give you this. But now imagine it as like this. This thing here is the same as this, d by dx of x to the power of minus n. Okay, because earlier we started with x to the power of n, x to the power of minus n, and then we rewrote it as x to the power of 1 over x to the power of n. We started with this, and then we turned into this. So now we're here. Let's look at it like this. Okay, hang on. So we got to hang on. We got to this stage here, and then we're going to reimagine this as this. Now, if you look at this here, if you want to differentiate this thing here, now look at this. You move this down here. That happens to be this, and then the n itself here, which is this bit here, gets minus by 1. So that goes to show that if you want to differentiate, if you want to differentiate x x to the power of minus n here, then you move this down here. So that will give you this thing here, and then the minus n itself gets minus by 1. That's this thing here. So this n here, you see the key to understanding this bit here is quite confusing. When you got to this stage here, when you get to this stage here, it equals this thing here. But then visualize this thing as x to the power of minus n. So by you visualizing this equals this thing here, you can see that this moves down here. That's this minus n here, and then the minus n itself gets minus by 1. So therefore you know, well, starting from this, you can use a quotient rule, and the quotient rule takes you to this. And then from this, you can see that, well, you move the minus n down here, and then the minus n gets minus by 1. So you start out with you start out with this here, x to the power of minus n here. Use a quotient rule, it will take you to this. And then from this stage here, you can see that this gets moved down here, and then the minus n itself gets minus by 1. So look, this thing here gets minus by 1. Okay, so it does go to show that even if you have x to the power of a minus number, this thing here will still work. Okay, yeah. So hang on. So this thing here will we can now see that this thing here will work even if n is a negative number. Even if you have minus 1, minus 2, minus 3, minus 4, and so on here, this will always work even if you have a minus number. The next video, well, at a later time, I'm going to show why this works even if you have to the power of a fraction. So suppose you have 3 over 7, it will still work. At the moment, I'm asking you to just accept that when you differentiate x to the power of 3 over 7, when you differentiate it, it will be 3 over 7, and then x to the power of 3 over 7 minus 1. I've always asked you to accept this, but in the next, well, at a later time, we're going to see why this thing here will still work even if n is a fraction. Okay.